Hello everyone, welcome to DualSense presentation. My name is Balakishore Elampalli and I am the principal investigator on this project. We are developing a simple, compact, automated sensor to monitor the health of a cross-deck pendant on aircraft arresting gear system used on aircraft carriers. This project is sponsored by the Naval Air Systems Command, NAVAIR, and the topic number is N202-119. First, a little bit about DualSense LLC. We are a small business focused on research and development of novel sensors and sensor systems. As an example, our team members have worked on deep ultraviolet lasers, standoff detection systems for trace explosives and chemicals, detection and identification of unexploded ordnances, and our most recent project on cross-deck pendant health monitoring. Our technology focus area primarily tends to be centered around optics and ultrasound. Our sensor systems have a combination of sensors within them and use artificial intelligence and machine learning tools to infer useful information from the sensors. With our engineering capabilities, we focus on primarily designing and building sensor prototypes and the system integration of those sensors. In addition, we have significant in-house capability to design and build electronics and optics. Cross-deck pendant or CDP is a steel rope that is strung across the deck of a landing area and is used to catch or decelerate the landing aircraft on aircraft carriers. The CDP spans the deck and on either side, purchase cables are attached which pass through pulleys as seen in the picture here. The purchase cables go under the deck and are attached to a pneumatic system. If you have seen one of those videos where an aircraft is landing on a ship, you can see them catching the CDP cable. You would have noticed in slow motion how much tension and strain these cables are under. Although these cables are 1.5 inches in diameter, they just flop around like a piece of thread. This is because they undergo extreme amount of stress and as a result are prone to small breaks or kinks and deformations. The current method of inspection of CDP cable is manual, requiring sailors to inspect different regions of the cable with their hands and eyes. This is a very subjective test and not a very repeatable process and very dependent on the operations training and experience. This makes it prone to error and waste. Generally, inspection of CDP is problematic and challenging to automate, and this is mainly because of the very complex set of conditions that CDP is used in. This slide summarizes various laboratory techniques that are used to inspect wire ropes in general. X-rays, ultrasound, strobe photography, thermal imaging, radio frequency, and magnetic flux methods are generally used. Most of these techniques have limitations for CDP inspection. For example, CDP is a steel wire on a steel deck, which means there is electrical contact, and because of this, techniques based on radio frequency are very hard to implement and generally do not work. The cable is usually applied with preservation or grease to protect it from environmental factors such as humidity, salt, water environment, and is resting on leaf springs close to the deck with physical access limitations. This makes the photography and thermal imaging hard to implement. X-ray methods require high energy equipment and are not practical in the field. Magnetic flux method does not work on all materials and the instrument needs to be moved along the length of the cable. Our technique is a type of ultrasound technique using very low frequency guided waves, and it overcomes limitations of conventional currently available higher frequency methods. The key operational need for the Navy is a compact device that inspects the CDP in place with very high accuracy and produces a simple pass-fail decision with high reliability. In addition, this device needs to be very easy to use by technicians on the deck, and this device should not require technicians to make complex interpretations or decisions. Shown here is an example illustration of a device which is attached to the cable with a readout unit. First, the concept of operations of how the device is used is illustrated here. This is a very simplistic depiction of what is happening within the instrument. The CDP is usually in its ready-to-use position, and the technician attaches the sensor head to the CDP and engages the instrument. With the push of a button, the instrument performs inspection and produces a simple pass-fail answer. While this is a simple process, what is happening behind the scenes of the sensor is a little more complex. The sensor head has a piezo element that generate ultrasound, and the ultrasound travels as guided waves through the steel cable, and whenever they encounter any deformations or breaks, there are some reflections that come back. These reflections are picked up by the receiver in the sensor head and then analyzed to determine the location and type of fault. Our instrument has sophisticated pulse shapes for signal that is transmitted, and the piezo receiver are positioned to optimize the received signals. This is an example of a measurement on a 5 feet long CDP section. You can see transmit and receive locations that are positioned close, approximately a few inches apart. The bottom of the slide shows measurement results. The x-axis of the chart shows progress in time, and the y-axis represents different epochs that are stacked on top of each other. As the guided wave propagates, it undergoes reflections or passes through the receiver, which can be seen on the CDP. First, the straight-through transmit beam is seen, followed by one of the reflections from one end, then reflections from the cut. Following that, the reflections from the second end of the 5 feet long cable can be seen. On top of this, multiple reflections from these ends that are going back and forth can also be seen and identified in the measurement. And similarly, these measurements can show us the detection sensitivity is high. Separately, we had measurements that show high sensitivity on this instrument. We were also able to show the measurement technique can extract several orders of magnitude smaller received signal compared to the transmit signal. In our phase 1 work, we were also able to show detection of a single wire break in an experiment. Next, our milestones and schedule. As I mentioned before, in phase 1, we studied the ultrasonic guided wave phenomenology and showed the feasibility of using ultrasonic guided waves for measurement on the CDP. Later, we performed laboratory proof of concept experiments and showed that the technique works on 5 feet long CDP sections as an example. These experiments were done in phase 1 and the ending TRL level was 3. More recently, in the phase 2 effort, we are working on a 30 feet long cable and showed some very encouraging results. These measurements are expected to bring the TRL level to 4. Following this proof of concept measurements, we plan to build 3 different prototypes. The first prototype is expected to be built early next year, where the goal is to demonstrate measurements on several different CDP cables, showing ultrasound-based detection of defects. And this will bring the TRL level of the sensor to 5. Following that, prototypes 2 and 3 will improve on the first prototype and make the instrument compact and man-portable. We will perform demonstrations on full-length cables, bringing the TRL level to 6. The final prototype will be made rugged for the environment and will demonstrate on full-length cables in a relevant environment. This final prototype will be delivered to the Navy. There are several benefits of using this sensor. Since we use ultrasonic guided waves, the factors that I mentioned earlier, like electrical contact with the deck, grease, and complex environmental factors, do not affect our measurement. This means CDP can be inspected without taking it out of service or needing to clean the CDP section. As I mentioned before, we have tailored our transmit signals and the sensor location elements to improve our sensitivity. Because of improvements to the sensitivity, we can measure very minute signals, and this enables us to measure longer distances or small breaks. Further, our clamshell design allows rapid attachment and ease of use for the technician. We are currently working on an advanced algorithm with this device, which is expected to enable simple go-no-go decisions. Our transition plan has three steps. Our first step is to meet the phase 2 milestones that I just described, and an advanced prototype will be created and delivered to the Navy in 2025. This will be a full system ruggedized prototype. However, no environmental test will be performed in phase 2. Following this, our next step is to seek funding from NAVAIR or PMA 251 to finish ruggedization of the product and perform environmental qualification tests. These tests will be done beyond the phase 2. Finally, once these tests are done, the product will be ready for direct acquisition by the Navy. In addition to inspection of cross-deck pendant cables for the Navy, we believe there are several civilian and industrial market opportunities for the sensor that we have developed here. Several applications that we have identified include construction of bridges. Several bridges around the world use wire ropes. Elevators, cranes, overhead hoists, ski lifts, ship moorings, and oil rigs. They all use various types of wire rope cables. We believe that this wire rope health monitoring sensor can be adopted for those applications as well by properly making the appropriate changes specific to these applications. With this in mind, we believe there is a significant opportunity for the wire rope health monitoring sensors to go beyond the cross-deck pendant. Finally, I want to mention that we are looking for partnerships, especially for three main purposes. The first is to expand the sensor application into those commercial markets. Second is to handle the full production manufacturing. We already have some ties with partners who can help us with low volume manufacturing, but will need help to scale it. And finally, if we find that it is necessary or useful at a later point, we may transition this product to the Navy's program of record. Thank you very much for your interest in this presentation. If you have any questions or have any interest in this technology, please contact me at my email address shown here. Thank you very much.